SwayamPrabha. Digital India. Educated India.
Welcome back. Previous video we looked at the brief history of polymers as well as their characteristics and applications. In this video we look at the structure of polymers. Bear in mind we are not looking at the chemistry aspect of these polymers, but we are looking at the polymer structure to understand the mechanical behavior of these polymers. So let us start by looking into what is the structure of a single polymer chain. For this we will pick an example of a simple polymer, polyethylene, which is C2H4. So this polyethylene is made using monomer called ethylene. So what we see here is an unsaturated ethylene. We call it unsaturated because it has two bonds between the carbon atoms. Ethylene is a stable monomer, but once it is in the presence of a catalyst with heat as well as pressure, then this double bond breaks into two active bonds. This is now called as the saturated ethylene or the saturated monomer because it has two active bonds to the left and to the right. When we have many of these active monomers or the active ethylenes, they all join together to form a polymer chain, which we see here. So here we have seen a single mer unit, which is a single molecule of ethylene, but because they are now saturated, meaning they have two active bonds, they join together with other mer units and then form a long polymer chain. So what we are seeing is polymers are large chain like molecules made from small molecules called monomers. Another aspect of these polymers is these are large molecules with covalently bonded backbone of carbon atoms. So if you look here, there is a carbon atom here, there is a carbon-carbon bond. So all of these are the backbone which give the strength to the polymer, because the bond between carbon and carbon is a covalent bond, which is a primary or a strong bond. This gives the strength to the polymer chain. So in previous slide we have seen the process of chemically combining monomers to polymers. This process is called as polymerization. There are two different polymerizations. One is a homopolymer, which we have already seen in the previous slide. So what are these? These are polymers with only one type of monomer units. So we only have ethylene in the case of polyethylenes. There are other examples like polypropylene and polyvinyl chloride, which also fall into this category of homopolymers. The second category is these copolymers. What we mean is, in these we have two or more types of monomers, so with chemical compositions. So for example is this acrylonitrile butadiene styrene, shortly called as ABS. This is a polymer used in 3D printing, and this is also used to make these building blocks of Lego. Another example is nylon, which we have seen in the previous video, where we said nylon is used for fabrics or to make ropes. But what is the characteristics of these copolymers? They have two chemicals, let us call them as A and B, and they form a chain. In this example I have shown this chain in a very orderly fashion, which if we focus on the B here, they are alternating. So these are called alternating copolymers. But we can also have random copolymers, meaning these A's and B's are randomly placed along the chain. There is a third combination called as block copolymers, where a couple of B's or couple of A's, they all join together and this form a block which is then attached to the chain. So this should give you an idea about how we polymerize. There is another name for polymerization called curing. So when we say we are curing a polymer, we mean that we are going from the monomer to the polymer. Usually these polymers, when they form, usually if the chains are long, they are in a solid state with showing some mechanical properties. Now let us look at what is the shape of this polymer chain. The schematic here shows that as though it is a very straight chain, but in reality what we see is something like this. So, this is an AFM image taken of individual polymer chains floating in a liquid. So, as you can see here, these chains have taken a very random shape. They twist, twirl and take these random shapes. Now, let us understand why it takes a shape so random. This is explained using this rotation of carbon molecules. So, if we see these two carbon bonds, there is an angle theta which is about 110 degrees. So, this angle is more or less fixed, but what is possible is the rotation. So, let us say this is one carbon bond and this is another carbon bond. Though this angle is 110, it can be in any of these orientations. So, there are several possibilities. So, meaning that this carbon atom can also be any place on this cone. Okay. We have seen here only two carbon bonds, but if there are multiple carbon bonds, then there are several possibilities this chain can take, because this particular carbon atom can be anywhere on this cone. Similarly, this carbon atom can be anywhere on this cone, and it is not like they take a position and they stay there, they are free to rotate as well. Because of this, they take this random shape, and this explains what we see in this AFM image. But now let us ask a question like, if we hold two ends of this polymer chain and pull them apart or stretch them, what shape does it take? Does it take a straight line as shown in the top left figure here? The answer is no. What it takes is a zigzag shape as shown here. So, it is a zigzag shape because these carbon atoms go up, down in this fashion. The reason is because the angle here between two carbon atoms is fixed and which is about 110 degrees. So, if you stretch and apply load, maybe that 110 degree can increase a little bit, but when you unload, it is elastic and it will come back. But there is only a slight deviation from this angle. So, this should explain us how a polymer chain structure is formed, or in the sense what shape it takes. Now, let us look at another interesting aspect of polymers called as functionality. Now, let us first define what this functionality means. It is the number of bonds a monomer forms with other monomers. So, if we think of an example of polyethylene, how many bonds did it form with other monomers? It was forming one to the left and one to the right. So, it has two number of bonds, we call it bifunctionality. So, here is the polyethylene monomer, and we have seen that it has one to the left and one to the right. Like this, we have many other functionalities. We see this monofunctionality, meaning that there is only one functional bond. These are also called as terminators. We will see in a while why they are called as terminators. And we have this trifunctionality, meaning they have three functional bonds. So, usually it can also have more than 3, so 3 and more we call it as polyfunctional as well. Okay. So, now with some examples, let me show you how we can form different kinds of polymer chains. The first is a linear chain. As you can see here, these blues are the bifunctional like the polyethylene example, but towards the end we have this monofunctional or the terminator. What is the terminator doing? Since it is only one functional, it bonds with one polyethylene and there is nothing else it does to the other end. So, which means it acts as a terminator. So, we have two terminators, one on each end of this polymer chain. So, let me pose a small question to you. What happens if we have a very small fraction of these terminators added to this polymer solution? So, if we have very few terminators, then what it means is you can form less number of polymer chains. If we are forming less number of polymer chains, then we should expect that the length of these polymer chains are very long. Okay. And you can as well say what happens if I do not add these terminators. So, what will happen? These polyethylenes can form a chain, because then the two ends join by themselves and they form a chain. But once you add terminators, then you have these open chains. But the other extreme is what happens if you have more and more terminators. If you have more and more terminators, then we have more and more polymer chains, meaning that the average length of these polymer chains are small. So, whether the length of the polymer chain is small or large is very important, because it really influences the properties of the polymers. Usually, when you have large polymer chains, they are stronger or stiffer. So, now let us look at another possibility. Here what we are showing it is a branched chain. Here, in addition to these bifunctionals and the terminators, we also have this trifunctional. So, here is the trifunctional, and because of this trifunctional, if you focus on the left of the trifunctional, it is almost like a linear chain, but to the right, because there are two branches it is taking, one goes to the left and one goes to the upwards and downwards. So, it branches out to two different chains. So, these are called as the branched chains, and we will see later whether if you have a linear chain versus a branched chain, how it affects the mechanical behavior of polymers. We will now discuss about the bonding between polymers, because there are two extremes. One is the primary bonds and the other is the secondary bonds. The way we differentiate between them is by their dissociation energy. What is dissociation energy? It is the energy required to separate two molecules. Let us say we have two molecules close by, and now we supply energy to move them apart, such that after separation the attraction between them is negligible. So, this amount of energy which is required to move them apart is called the dissociation energy. So, primary bonds are those where this dissociation energy is large. So, which means you need to supply a large amount of energy to move them apart, whereas in secondary bonds this energy is very less. So, now let us look at few examples of primary and secondary bonds. So, in primary bonds we have metallics, covalent and ionic bonds, but in the case of polymers usually we are only focused on covalent bonds, because metallic and ionic are very rarely seen. A rare example is polymers are usually low conductors, but how do we increase the conductivity? We can add some small metallic particles into it. So, when we add these metallic particles, that is when we have these metallic bonds, but otherwise mostly speaking they have these covalent bonds. Moving to secondary bonds, we have hydrogen bonds, dipole and van der Waals forces. As you notice, so the covalent bonds have between 50 to 200 kilocalories per mole, this is the dissociation energy. But when we move to the secondary bonds, this is in the range of 3 to 7 for hydrogen, 1.5 to 3 for dipole, and it is very less in the order of 0.5 to 2 for van der Waals forces. So, what it means is if a polymer has, let us say, both primary and secondary bonds and you are supplying energy in the form of heat, let us say, then the first things to break or melt are the secondary bonds, because the amount of energy it takes to break them is small. But if you supply more and more energy, eventually there is sufficient energy to even break these covalent bonds. Okay. So, the reason why we have studied about this bonding is, now we will look at how, if we have multiple polymer chains, how they coexist or what kind of bonds do they have. So, we are talking about coexistence of multiple chains. So, we will be looking at linear polymers and cross-linked polymers. Linear polymers are ones with secondary bonds between the chains. So, if you focus here, let us say this is chain 1 and this is chain 2, they are crossing over, and at this crossover the kind of bond between them is simply a secondary bond, which is very weak, and if you supply a little energy it breaks. So, what happens if you supply that energy after it breaks, these polymers are free to move around, they are not stuck to each other. Another extreme is the cross-linked polymers, where between these two polymer chains we have a primary bond, usually a covalent bond. So, since we have already seen the primary bonds or the covalent bonds need very high energy, usually it is very hard to break these bonds, or it is very hard to break these chains apart. So, we will see later in the next video how this affects the mechanical behavior, or how do we get different polymers depending on whether it takes a secondary or a primary bond between them. So, let us summarize this video. We started by defining what a polymerization is, saying that it chemically combines monomers into polymers. Then we looked at single chain polymers. So, we understood what is the covalent bond which acts as a backbone for the carbon atoms. So, we said because of the strong carbon atoms bonds which is covalent, it is very strong and it acts as a backbone for the polymers. And we have also seen why it takes a zigzag shape when we try to hold two ends of the polymer chain and stretch it. That is again because of the angle between two carbon bonds which is close to 110 degrees. We have also seen how multiple chains coexist. We said they can either have a primary bond between two chains or a secondary bond. Linear polymers are when they have secondary bonds between them, and the cross-linked polymers are those where there is a primary or a covalent bond between them. So, with this let us conclude this video, and in the next video we will look at what are the classification of these polymers, and we will use these primary secondary bonds to help us do the classification. See you.